Imagine a weather anchor pacing across the studio, and behind them, there's this massive, photorealistic, virtual hurricane perfectly tracking their every single move.
Yeah, like if the physical camera tilts up, the virtual sky tilts right up with it.
Right, there's not a single millimeter of lag. So how does a control room actually pull that off?
Well, they do it with hardware that speaks, the exact same language as virtual reality.
And that is exactly what we are looking at today. Welcome to your deep dive. We are focusing on a very specific piece of hardware, the Bolin Technology R9-230NX PTZ, or pan-tilt zoom camera.
Well, we've got this incredibly dense spec sheet from HDTVSupply in front of us.
Yeah, and our mission today is to cut through all that technical jargon and figure out what exactly justifies this camera's, frankly, eye-watering $4,895 price tag.
Because almost $5,000 for a single PTZ camera is...
It's a lot. So, okay, let's unpack this. Looking at this spec sheet is kind of like looking under the hood of a race car, right?
Yeah.
Like, we really need to ignore the cup holders and just focus on the engine. Because on paper, some of these specs almost look like typos.
They do. I mean, they really require some context to make sense of the value proposition here.
Exactly. So let's look at the raw visual power first before we get into the virtual stuff. For example, this camera shoots in 1080p. Wait, almost $4,800 for just 1080p? I mean, I can go buy a 4K camera at a big box store for like a fraction of that.
Yeah, you totally can.
So with everyone obsessing over 4K or 8K resolution, does the market actually prioritize this lower resolution for live broadcasts?
Well, it basically comes down to a fundamental trade-off in physics. It's a balance between packing in pixels and actually capturing light. This camera uses a Sony one over 1.8-inch Starvis 2 sensor.
Okay, so a highly specialized sensor.
Right, and it's only a 4-megapixel sensor. If you try to cram 4K resolution, which is, over 8 million pixels, onto a standard sensor, each individual pixel has to be microscopic.
Because they all have to squeeze into the same physical footprint.
Exactly. And tiny pixels just don't catch much light. But by sticking to 1080p on a relatively large sensor, each individual pixel on this Bolin camera is physically much, much bigger.
Ah, I see. So they act like larger buckets catching more rain, or in this case, catching more light.
Precisely. And that is why this camera boasts an extreme low light rating of 0.00008 lux.
Wait, 0.00008.
Yeah, and to put that in perspective for you, that is roughly equivalent to the illumination of a moonless, heavily overcast night.
Oh, wow.
So even in near total darkness, what's fascinating here is that those large pixels gather enough photons to reproduce faithful, crystal clear 1080p video at 60 frames per second.
That is wild. It perfectly explains the low light color performance.
Yeah.
But looking at the sheet, it also highlights a 30x high-resolution optical zoom and this, quote, super image stabilizer. Now, a massive 30x zoom means you could be mounted at the very back of a sports stadium and still get a super tight shot of the quarterback's face.
You definitely could, yeah.
But at that distance, I mean, even a slight breeze shaking them out would normally make the footage completely unwatchable, right?
Right, and what's really cool here is how the camera physically fights that shade. The super image stabilizer isn't just, cropping your video digitally to hide the bounce.
Like the digital stabilization on a smartphone.
Exactly. Instead, it uses internal gyroscopic sensors to detect the exact frequency of the vibration. Then physical micromotors instantly shift the optical glass elements inside the lens in the exact opposite direction.
Just to cancel the movement out entirely.
Yes, exactly.
Okay, so the hardware ensures that your raw video feed, the baseband video, is perfectly lit and rock solid. But as you mentioned earlier, the real justification for the premium price tag is how this camera talks to digital environments.
Yeah, that happens through a feature called the FHD protocol that stands for free-dimensional video.
Free-dimensional video, okay.
Right. And this is what transforms the camera from just a fancy recording device into an automated bridge for augmented and virtual reality, which is used in weather reporting, sports, news, live events.
Here's where it gets really interesting, though. How does a physical camera actually tell a computer where it's looking?
Well, as the PTZ camera physically pans or tilts or zooms, that FHD protocol translates the exact physical position of those internal gears into raw mathematical data.
So it's tracking the actual mechanical movement.
Exactly. It continuously outputs its precise X, Y, and Z axis coordinates. And this data is sent out over the network simultaneously with the video feed with ultra-low latency.
It's essentially giving the camera A real-time GPS coordinate system, like perfectly syncing physical tracking with the digital world. It takes physical mechanics, literal gears turning, and turns them into math.
Yeah, and if we connect this to the bigger picture, graphics engines like Unreal Engine read that math.
Right, so they know exactly what the camera's doing.
Yes. So when a broadcaster wants to overlay 3D graphics like that virtual hurricane we talked about, or a digital first down line on a live football field, the engine knows exactly where the physical lens is pointing.
And how tightly it zoomed in. So the digital storm clouds pan at the exact same speed as the physical camera.
Precisely. It completely eliminates that awkward, floaty disconnect between the real physical lens and the digital graphic. The physical and digital environments are seamlessly blended together.
So what does this all mean for you listening? Well, if you are producing live events, this isn't just a camera. You aren't just buying something to capture a speaker on a stage. You're buying an automated, ultra-reliable bridge that maps the physical world directly into a VR or AR production engine.
Yeah, you're paying for flawless mechanics that can handle terrible lighting and shaky conditions while seamlessly building immersive worlds right around your broadcast.
It really makes that price tag make a lot more sense, honestly. And it leaves me with one final thought for you to ponder. If a single pan-tilt-zoom camera can now perfectly map its physical movements into a 3D virtual environment in real time, just how soon until the line between a physical live broadcast and a fully rendered digital world disappears entirely?